Mars in 30 years. You cannot get to Mars in 20 years. If you want to go to Mars, you've got to do it in 10 years or less from program start, or you're more or less guaranteeing that the political conditions that allowed you to launch the program will not remain in place long enough for you to pull it off. Okay? So this thing where someone says, oh, we're going to Mars, we got it on the planning chart for 2054. I mean, that's not a Mars program. That's baloney. Okay? If you want to go to Mars, you commit to Mars. You do what Kennedy did in '61. You're saying, I'm committing the nation, and basically, I'm going to do this by the end of my second term. Okay? And that's what Obama has to do. If we're going to have a real space program, the American people want and deserve a space program that is really going somewhere. And that is what is needed to do it. Okay? Now, from the technical point of view, can this really be done by the end of Obama's second term? Can we have humans on Mars by 2016? Okay, which is 7 years from now. Well, I can give you the short answer by pointing out that it only took 3.5 years to win World War II. Okay, so if you can do something, you can do it in 7 or 8 years. Or, as Kennedy Johnson did, more or less have it almost done so that the actual follow-through was in the cards. But, I mean, do we need the Battlestar Galactica to go to Mars? No, we don't, okay? Look, if you do this right, if you're not doing this in order to justify someone's Battlestar Galactica program, there are ways to do this. Now, I'm going to show you the plan. It's called the Mars Direct Plan. And I'll show you it as it was designed back in 1990. It's working for Mr. Augustine, who has kindly invited me to come to his committee to talk. But look, you do need a heavy lift booster. Anyone who wants to cancel the heavy lift booster is saying we're not going anywhere. Now, there's this controversy right now between the Ares 5 people, which is Griffin's design, and Direct people, which is another group. It doesn't really matter. Okay, what matters is we get a heavy lift vehicle. Now, this is the one we designed back in 1990, which we did call the Ares, and it's shuttle derived. Okay, the reason why the engines are offset in that odd way was this was anticipated that it would be using the shuttle launch pads, which have their flame trenches offset in just that manner. But if the shuttle is retired, you'd obviously put them underneath and get somewhat better performance. But with a shuttle core, couple of solids, and a hydrogen-oxygen upper stage, you can create a Saturn V equivalent vehicle, a vehicle capable of lifting 120 tons to low Earth orbit, or using that upper stage, which is basically the equivalent to the S-4B, the third stage on the Saturn V, to throw about 47 tons on a direct trajectory to Mars, or 59 to the moon if you would care to do that. Okay, and that's how we did Apollo: lift and throw and let it go. Okay, you don't have to do on-orbit assembly or even an on-orbit rendezvous. You just have a booster that throws the payload to the planet with the same upper stage of the same booster that lifted it to orbit in the first place. That's how we've done every real unmanned planetary mission we've ever done. That's how we did the real Apollo missions. If we ever tried to do, Cassini by launching little rockets to Earth orbit and assembling payloads and this and that at a spaceport, we never would have gone, okay? Just launch it and throw it if you want to do it. Now, if you have a vehicle like that, it happens that we do need, if we're going to Mars, to do 2 launches per mission, and this shows the mission sequence. Okay, year 1, 3, 5. If we got serious about this, year 1 on this chart could be 2014, year 3 could be 2016. Okay, year 1, we launch one of these boosters off the Cape. We use it to throw an unmanned payload on, actually, I should say unpiloted payload. This is politically correct language. On a direct trajectory to Mars. It takes 8 months to get there on a minimum energy trajectory. Uses an aero shield to aero capture into Earth orbit, And then once it is captured and we have a little time to check out the weather and make sure everything's good, we bring it back into the atmosphere, use the aeroshell to slow us down now all the way to subsonic speeds, and we pop a parachute, come down slow, put ourselves down soft on the Martian surface with rockets, just like we did with the Viking mission in 1976, and we're even able to do again with the Phoenix lander last year, showing that we still could do what we once could do. So now you've got this thing that's been put on Mars. Now, what is this that is sitting on Mars? Well, the payload consists of a number of things. The primary object is the Earth Return Vehicle, ERV, which is a little rocket ship. It's got a small cabin with 15 feet diameter, tight quarters for a crew of 4 on a six-month transit from Mars back to Earth in the final leg of the mission, but no one's in it now. Then you've got 2 methane oxygen rocket propulsion stages, chemical rocket propulsion stages, which, however, are unfueled. They got to be unfueled, or this thing would weigh 4 times as much as it does. It would be much too heavy for an Ares or a Saturn V equivalent vehicle to throw to Mars. However, in some of the lower stage tanks that are later going to contain methane, we got about 6 tons of liquid hydrogen, probably in gelled form, and then slung below the vehicle, not shown in this diagram, is a light truck, like a little pickup. Sitting in the back of that is a 100 kilowatt nuclear reactor. The thing's landed on Mars. The truck is telerobotically driven a few hundred yards away, unwinding a cable off the back of it as it goes, and then the reactor is put on the ground and starts to produce power. And what you do then, back at the ship, is you run a pump and you suck in the Martian air, which is 95% carbon dioxide. You can react the carbon dioxide with hydrogen, the hydrogen we brought from Earth. They will react over a catalyst exothermically to produce methane and water. The methane is our rocket fuel. The water we take, we electrolyze. Hydrogen, oxygen. The oxygen is our oxidizer. The hydrogen recycled to make more methane, and so forth. And then to get additional oxygen, which we want to burn our methane at its best mixture ratio, we take carbon dioxide and we split it into carbon monoxide and oxygen. The oxygen we store as useful rocket propellant. The carbon monoxide we vent as waste. You can do that on Mars. There's no EPA there. And so when you're all done, what you've managed to do is turn 6 tons of hydrogen brought from Earth into 108 tons of methane oxygen rocket propellant on the surface of leverage of 18 to 1. Okay, it's like a pioneer being able to acquire the useful mass of a bison for the transported mass of several bullets and cartridges. And that's what makes the whole mission sing. 95% of your return propellant's coming from Mars, only 5% had to come from Earth. And because we can make propellant with so much leverage, we make extra to allow us to use ground vehicles on Mars that use chemical fuels, which is a tremendous advantage for exploration, since chemically powered ground vehicles have a much higher power to mass ratio than you can get with battery powered vehicles. That's why they're so much more popular here on Earth. That's why people use gasoline cars instead of electric cars. And in a frontier environment like Mars, you really do want that extra power, range, hauling capability, and all-around muscle that you have from having a real car instead of a golf cart. But it wouldn't be practical unless you can make your fuel on Mars, which you can. So the key thing here is the ability to make use of Martian resources is the key to not only making the mission cheap, it's also key to making it effective, which is equally important, because there's no point going to Mars unless you can do something useful once you get there. So after the propellant's been made on Mars, at the next launch opportunity, 2016, we launched 2 more of these boosters off the Cape. One shoots out another one of the Earth Return Vehicle fuel factory deals. The other shoots out a HAB module with a crew of 4 in it. Okay. The cab is basically a tuna can HAB, not unlike in architecture the HAB modules that we use at our Arctic station and our desert station. 2 decks, each with 8 feet of headroom. These we fit out with 4 bunks. Our desert and Arctic stations we fit out with 6. But the reason why I push for 4 is not because I prefer 4 to 6, but because I believe the question of whether this mission happens or not is not going to be determined by whether we have a preferable number of crew members, by whether we can afford the mission. And the cost of the whole program is going to scale up with the crew size. So the question is not what is the most desirable crew size, which might well be 6 or 7, but what is the minimum crew size that we can do the mission with and still do it competently. And I believe that is 4 for the simple reason that that allows you to divide the crew up into 2 groups with no one being alone. Okay. Here it is. I won't go into the design of it, except to note that, well, you have 4 little staterooms, a number of public areas, science, galley, and so forth, and in the center is a solar flare storm shelter, where